Hi, a very good morning. My name is Zheng Chua. I'm from the National University of Singapore. Today I'll be presenting the paper Neural Networks Can Learn Function Type Signatures from Binaries. This is a joint work with my co-authors Shiqi, Shen, Prateek, Saxena, and Zhenkai, Liang. So binary analysis has always been central to system security, of which function recovery forms the basis of many security applications. Function recovery and the information derived from it can be used in tasks such as binary hardening, enforcing CFI, and function matching for vulnerability detection. Given how important function recovery is, how is it done by a typical human analyst now? Well, the first step to function recovery is to determine where is the function. So the boundaries, the function boundaries define the actual size and content of the function, of which the analyst can base its analysis on. Here, the analyst can make use of intuition and heuristics to identify said boundaries, like function prologues and epilogues. Bao et al. And Shen et al. Have also shown how machine learning can be used to identify these function boundaries. So after we have identified the function boundaries, next would be to recover the function signatures and most notably the function argument counts and types. Before we even start with our analysis, the analysts have to make sense of the instructions found in the function. This is dependent on how much experience or knowledge the analysts have on that particular ISA. So depending on how much experience the analysts have, this might end up being a long read of Intel's software developers manual. I mean, I spent a lot of time reading this. So after the long hours of reading, we can finally make sense of what this function does. And with that all out of the way, the analyst can finally begin his or her analysis. Well, the first part of recovering the argument types, argument signature is to recover how many arguments there are. In order to do that, the analyst must first know what is the calling convention which is used by the binary. This relies on specific domain knowledge of the ABI that is used by the binary or the function. Now, since this example function comes from an AMD 64 Linux binary, it's a reasonable assumption to kind of like guess that this function uses the System 5 AMD 64 ABI. As such, seeing how the registers RDI and RSI are being used before they are defined within the function, the analyst may make the prediction that, maybe there are two arguments being used in this function. Now, after knowing how many arguments there are in a particular function, the next step is to determine what are the types of the arguments. So this is typically achieved by observing how each argument is being used, and it involves the tracking of the flow of the data. Taking a look at how the first argument is being used, we can see how the data flows to a particular dereference operation. The analyst at this point of time might go like, there's a dereference of the value that is being passed as the first argument. Since only pointers are being dereferenced, maybe the first argument is of a pointer type. And we repeat this for the second argument. Taking a look at the second argument, we realize that it's being used in this particular instruction called divq. And me being the absolute noob in Intel ISA, I have to refer back to the manual and kind of like realize that this is an unsigned integer division, and hence I can make that prediction that, yeah, maybe it's the second argument is an integer type. So what are the problems with the approach that I've just described? A key problem is that this approach requires specific domain knowledge. And although previous works have shown that machine learning can help with function boundary identification, the recovery of the argument signature still relies on human experts, either directly or indirectly. Directly in the form of manual human analysis, and indirectly through the encoding of the knowledge into tools, heuristics, and algorithms. What this means is that there is a constant need to update the tools and knowledge base for each upcoming compiler or ISA. Given how hard it is to scale up human beings, I think all of us agree that human resource is scarce. can we actually solve this problem? Can we build a system to automatically do this? More specifically, can we actually make use of a neural network to emulate the learning process of a human analyst to solve this problem, and to do it in an explicable manner? So in this work, we show that this is indeed possible. We are the first to apply neural networks to the problem of recovering function argument signatures. We designed and implemented our prototype called EKLAVYA, and showed how even by just using a simple RNN, we are able to produce results that are comparable to heuristic-based methods currently employed. More importantly, we showed using analytical tools such as gradient-based saliency maps and analogy questions to try and understand how the model makes its decision. Using these tools, we showed through our work how neural nets can learn interesting concepts without explicit domain-specific knowledge from the user, like calling conventions and instruction semantics. With that, let's take a look at what the learning problem we are trying to solve. What we want is to have a model that takes as input a function and produces the argument signature, which consists of 1, the argument count, and 2, the argument types. Note that the function which is used as input is a sequence of instruction tokens, and these instruction tokens do not carry any semantic meaning. They just give each instruction a unique representation. So as for the outputs, I guess argument count is pretty self-explanatory. It's the number of arguments that a function has. As for the types that we are trying to recover in this work are C-stop types. They are not exactly C types. So they are classed into categories such as integers, pointers, characters, floating point numbers, etc. In order to train the model, we'll need a training set which consists of both the input and output. This input-output pairs forms the ground truth and is obtained by compiling the program with debug information and then subsequently extracting the relevant information from it. With that, the first question that we have is that, given that our instruction tokens have absolutely no semantics in it, can we actually learn the semantics of the instruction in an unsupervised manner? To that end, we made the embedding process explicit for EKLAVYA. The embedding module takes in the individual instruction token as described previously and produce a vector representing the token. Each of the instruction IDs can actually be represented as a sparse one-hot encoded vector, which can be multiplied with the embedding matrix to produce the resultant vector. The embedding matrix is learned using a neural network tasked with predicting what are the contextual instructions for any given instruction that is being embedded. The intuition or idea behind it is that the semantics of the instructions can be inferred from their contextual use in a normal benign program. It's very much similar to how the semantic meaning of words can be inferred from their contextual use in natural languages. So what exactly are these embedded vectors and how are they useful in our task? These vectors are actually representations of the instruction in a dense n-dimension space where distance between the instructions can potentially encode relationship. Take this for example. What we see here are two instructions that are being mapped into this, in this particular case, two-dimension space. So the direction in red actually represents the relationship between these two instructions. So, given this pair of instructions, one might want to find yet another pair of instructions that has a similar relationship as this particular pair. This is also known as an analogy question. Here we'll take a look at one of the examples found in the embedding that is produced by EKLAVYA. So given the instruction push ESI, what I want to do is to find the corresponding instruction such that this new pair has the same relationship as that of the old pair. We phrase this question in the form of a vector arithmetic on our learned embedding, and the result we have is pop ESI. So we can think of this as like pop EDI minus push EDI plus push minus push ESI equals to pop ESI. So what this means is that the pair push ESI and pop ESI has the same relationship as the pair push EDI and pop EDI. Given enough of these examples, we can actually come to the conclusion that this red arrow direction actually represents a the semantic meaning of the operation of a particular instruction. Similarly, we can pose the question in yet another form. In this case, the pair would be pop EDI, pop ESI, and then push EDI and find yet another instruction. It's not hard to see how the operand register of an instruction is also represented in a particular direction. Recall that we begin with each token having absolutely no semantic, and in the process of inferring contextual knowledge, contextual usage, we can actually recover these relationships between them. More examples of such analogy questions can actually be found in the paper if you're interested in it. With that, let's move on to the actual prediction part of EKLAVYA. EKLAVYA's prediction module takes a function in the form of a sequence of real-valued instruction vectors like that of what you have seen previously, and makes the prediction on the number of arguments and the types of arguments. The prediction module is a 3-layer single direction forward GRU RNN with dropout between the layers. It's a pretty standard RNN model. Each instruction vector is fed into the model in consecutive steps, and the prediction is made at the end. As one may observe, the instruction input of each step is actually combined with a hidden state, and this hidden state is what allows the network to have a notion of a memory. The hidden state accumulates the changes from the previous input steps and can be thought of as a summary of the useful information that should be kept. During training, what kind of information should be kept in the summary or training is done using backpropagation, much like other neural networks. Now that we have a model and a way to train the model and make predictions on how many function arguments there are and what are the types, the next question we have is, how did that model make that prediction? Is it making a random guess? Is it basing the prediction on the distribution of the data? Trying to understand how a human analyst makes a prediction is simple. You just have to walk up to that guy or girl and ask the person, how do you know that the function have 2 arguments? Now, it's pretty much impossible for us to ask the model to directly explain itself. At least currently, it's pretty much impossible. So what can we do? Well, we can ask the model this question. What are the important parts of the input which the model actually used to make the prediction? You might ask, how would that actually help us in understanding how the model works and how the model makes the prediction? Take this picture, for example. The picture highlights the parts of the image which is important to the model in making the prediction that this image is a dog. Now, at the same time, we can also make a highlight of the important parts of the image in which we feel it's important in trying to make the prediction that this image is of a dog. Now, the comparison between these 2 importance highlight enable us to form a hypothesis on how the model actually makes this prediction. Given enough of such examples, we can use inductive reasoning to try and explain what the model is doing. So how do we get the importance of the model? The importance of an input is really how influential it is on the final prediction, and this translates to the rate of change of the output with respect to that of the input. This is essentially the gradient. So by calculating the gradient, this allows us to quantitatively measure the importance of an input or sequence of input on the final output, which can be used to create a saliency map, which is a map of how important each instruction is with respect to making a particular decision. So let's take a look at some examples that we have that's generated by EKLAVYA. Let's take a look at this function snippet. How will a human, more specifically, how will I make the decision that there are 5 arguments in this function? Using the knowledge gained previously on the ABI, the calling convention, I'll actually highlight this particular instruction and kind of like say that, it uses R8, the register R8, and hence this function have at least 5 arguments without any further without any further evidence or proofs, I will kind of like make the conclusion that this function has 5 arguments. And let's take a look at what is the saliency map that is generated by EKLAVYA. It actually coincides with what I use to make the prediction of the fact that the function has 5 arguments. Given enough of such examples and a diverse enough set of examples, we can kind of like reason that the model has indeed learned something akin to the calling convention of the function. Let's take a look at another example involving type recovery. In this particular case, the first argument of this function, of this particular function, is of type pointer. As a human analyst, I will actually focus on these 2 highlighted instructions. And I will see that the value of the first argument is being moved into EDX before it's being dereferenced in the subsequent instruction. Hence, with that, I can conclude that the first argument is of a pointer type. Like before, let's take a look at what the saliency map tells us, how the model makes that prediction. It pretty much concurs with what a human analyst would do. And with that, we can gain a certain level of confidence that the model is not making random guesses or making guesses based on the distribution of the data set. So to kind of like wrap it all up, EKLAVYA consists of 2 main modules, the embedding module and the prediction module, which corresponds to the 2 main functions we want to perform: learning instruction semantics and recovering argument signatures. This modular design of EKLAVYA allows it to be more explicable, since we can reason about each part separately and independently. And this modular approach allows the individual parts to be swapped out for a better approach in the future if one can be found. Like maybe in the future, there's a better way to do instruction embeddings. So we can just replace the embedding module of EKLAVYA. Another possible use, another benefit of having a modular design is that the individual parts can actually be used in some other problem or use case. For example, the instruction embeddings that is generated by the embedding module might be actually useful in other binary analysis problem. So with that, we conclude the qualitative analysis of the results obtained from EKLAVYA and move on to the quantitative results. Before going into the results, let's take a look at the evaluation dataset which we used. The dataset is made out of 8 different Linux packages compiled with both GCC and Clang on optimization levels 0 to 03. We remove identical functions within the dataset by hashing the binary function, resulting in about 370,000 functions for each architecture. One might argue that this amount of sanitization should be enough, right? Well, not really. Binary functions can have different values even when they are the same due to binary dependent offsets. So for example, in this particular example, these 2 function snippets actually belongs to the same function but compiled in 2 different binaries. And because of the way how binaries are being compiled, the global variable found in this particular function has a different offset in both, and hence naively hashing the function is insufficient. In order to kind of like work around or solve this problem, we propose a very simple fix, or we use a very simple fix. What we did is to just remove all constants in the function before actually hashing it. So this is not a perfect solution, but it should suffice for our case. So with the sanitization performed, we have approximately 60,000 functions for each architecture, down from 370,000. This is about a 6 times reduction in the amount of functions that we have. This highlights how binaries can contain large amount of similar function, and if one is not careful with sanitization, this can have an effect on the accuracy by artificially inflating how good the approach is. With that said, we separate the sanitized data set by randomly selecting 80% of it as training set and the remaining 20% as testing set. So here I'll actually go through a brief summary on the accuracy results. From the actual numbers generated by EKLAVYA, we have seen that the accuracy of prediction on unoptimized binaries is higher than that of optimized binaries for counting tasks. And on the same note, the accuracy of predictions for AMD64 binaries is higher than that of x86. Accuracy of predictions of binaries compiled with clang and GCC are actually comparable. There's about a 1% difference between the accuracy, which is pretty much the same. And finally, the accuracy of predictions for infrequent classes that is found in our data set. For example, the number of functions with floating point numbers as an argument type only takes up about 1% of our data set. But the precision and recall on these rarely seen categories is actually relatively quite high for EKLAVYA. Now, due to time constraints, we actually look in detail on the first 2 points. Interested audience can refer to the paper for more details on the rest of the analysis. So what we see here is actually a graph of the accuracy that's plotted based on the optimization levels and the task that's being performed. We can see how for AMD64 type, that means the type recovery for AMD64 functions, the accuracy for O0 to O3 is about 80%, and it's pretty much stable across our optimization level. But when we actually take a look at count recovery, we can see how for O0, EKLAVYA has about 95% accuracy, and it drops sharply down to about 80% for any optimized binaries, that is O1 to O3. We can see a similar pattern for x86 too. And if you actually compare the two architectures, for example, AMD64 type and x86 type, you can see how the AMD64 type outperforms, EKLAVYA outperforms, the prediction that EKLAVYA makes on AMD64 types is higher across all optimization level compared to x86. The same can be said for counts. With that, I would like to conclude by saying that it is indeed possible for us to apply neural networks to binary analysis problems, and more importantly, apply it in an explicable manner. Further, it's also possible for us to extract instruction semantics based on its usage in normal benign compiled binaries. As we have seen on the sanitization slides, having a good data set is also very important, and one really has to take care on how the data set is being generated and how sanitization is being done. Finally, I would like to conclude that throughout the course of working on EKLAVYA, we have found many similarities between problems in binary analysis and natural language processing. And as such, we felt that this is a potential direction for future research on how can we apply machine learning techniques on binary analysis problem, and how can we use some of the tools that are used in NLP to explain the models that are learned in binary analysis problems. With that, I thank you all for your attention. You can actually grab the data set which we use and the code that we use in EKLAVYA in the following, in the link that's shown, and I'm open to questions. Yep.
If you have questions, please come to one of the microphones in the front of the room. And before you ask your question, please state your name and affiliation, please.
Hi, Petros Maniatis, Google Brain. I was wondering, there are lots of Linux packages and you chose 8. You could have chosen 8,000. What was the reason you stopped? I mean, more data is better, right, for machine learning?
Yes, more data is better, but we have to stop somewhere because we actually have to run our training and our, what's that called? Evaluation. So the way that we selected the 8 packages really is we begin with actually 3 packages, which is similar as previous work, and then we have extended our data set based on these 3 packages. Hence, we have these 8.
So training was the limiting factor in this case, time to train.
Yes.
I see. Thank you.
Kevin Borota, UC Santa Barbara. I'm wondering whether, given that you're already losing almost 20% of accuracy on recovering what your ground truth has, How does that compare to A, obfuscated binaries, which would be kind of evasive malware, and whether it's possible to recover functions which essentially use non-primitive data types?
Sorry, Prateek, can you repeat your question again?
Sure. So it's two parts. First, how does this work with evasive binaries, for instance, malware, which would be obfuscated? Would the approach there work too? How much accuracy do you think you might lose? And the second part of the question is, does the function type recovery also work for essentially higher order types, such as classes?
Okay. So regarding the first question, which is, can this work on obfuscated binaries? We have never tested it, so whatever that I say is based on my guess, on an educated guess. My guess would really be maybe, because it really depends on what you use to train the model. So for example, an analyst might, if an analyst is able to use some human intuition and heuristics to identify the types of an obfuscated binary, then my guess would be that our particular approach will work for it too. As for the accuracy, I really have no idea how much it would take, actually. As for the second one, sorry, what was the second part again?
That was about higher order types and essentially classes.
For that, based on our results, so we actually tried to recover the struct type. We don't really differentiate between different struct types, but rather we kind of like say that if the argument is of a struct type, say that it's of a struct. The result that we have is that we don't really have a lot of functions that take this kind of complex structure types as an argument. And most of the time what we take is actually a pointer to these structure types. Can neural networks recover such information? My guess is yes, because there's a certain pattern on how these structures are being accessed.
Thank you.
Yeah.
Sorry to interrupt. Due to the time limit, we may only have time for one question. And if you have other questions, you can probably ask the speaker offline. Go ahead.
Hi, Dongguang Kim from KAIST. So I have a question for the how to make the input set of instructions, because if you, for example, if there is 3 cores in a function, then some compiler optimization makes like they reuse the call saved registers. For example, if there is first argument is stored in the RDI register, and the second call, if there is no change in the same argument, then the second call will use the same register without storing another value. So
this is actually this is very common in actually optimized binaries, if I understand your question correctly. So it's something we call implicit argument passing, where the function that is being called will reuse the registers to pass it on to a function that function is calling. This is actually the reason why our model performs relatively, you see this huge drop in the accuracy between O0 and O1 to O3. So this is the reason, actually.
Yeah, I see. Thanks.
Yes.
Let's thank the speaker one more time.
Thank you.